Now the next point I have to discuss here is artificial transmutation. Artificial transmutation of elements. Artificial transmutation of element. First I define what is the meaning of artificial transmutation. First I define that one now. The conversion of one element into another by artificial means. By artificial means is called artificial transmutation. Artificial transmutation. Is called artificial transmutation. The meaning is like this. Artificial transmutation. One element is converted into another element is in the process of artificial means. That is called artificial means. It was discovered by Rutherford. It was discovered by Rutherford. It is possible, means artificial transmutation, it is possible. It is possible for elements whose atomic number less than 20. Atomic number is less than 20. This kind of process is possible. What is that? Artificial transmutation is possible. Artificial transmutation is possible. Now here what way these elements are converted, that one I am showing now. 7 nitrogen, 14. The basic state is stable state. That is now with respect to the helium. Then it goes to 18. That is oxygen. 17. It is also stable state. Plus hydrogen on H1. That is proton. These are the stable state and helium. Then it goes to the oxygen and hydrogen. That way the components are coming. Now, these are the points are relevant to the artificial transmutation of elements. Artificial transmutation of elements. Next, another one is nuclear fission. Nuclear fission. Another important one I have to write now. Nuclear fission. Fission. Nuclear fission. In the earlier point I described that nuclear fission. Once again I repeat the point. Now here nuclear fission means splitting of heavy nucleus. Splitting of heavy nucleus. splitting of heavy nucleus into lighter fragments. Splitting of heavy nucleus into lighter fragments and emitting large energy is called nuclear fission. The definition first I described the meaning of the nuclear fission. Here the point is heavy splits into multiple lighter and lighter. That is nothing but what? Nuclear fission. Now it was discovered by Hahn, H-A-H-N. It was explained by Bohr. It was explained by Bohr using liquid drop model. Using a liquid drop model, Bohr explained this. Liquid drop model of nucleus. Liquid drop model of nucleus. Next one now. Uranium-238. Next point. Uranium-238 undergoes fission. Uranium-238 undergoes fission with fast neutrons with fast neutrons that generated kinetic energy greater than 1 MeV. The generated kinetic energy is greater than 1 MeV. That will come. Uranium-238 undergoes fission process with fast neutrons and its kinetic energy is greater than 1 MeV. The same process in the slow neutron process now. That one also tell you here. Now after this you should write here. That is uranium. Possibility is there here. Yes. Uranium-238. Next point now. Uranium-238 undergoes bombarded with slow neutrons. Earlier one is fast. Now slow neutrons. With slow neutrons whose kinetic energy approximately equals to 0.025 electron volt. 0.025 electron volt. Note on that point. 0.025 electron volt. Next one now. Thorium-232 undergoes fission with fast neutrons. It is thorium, fast neutrons. Plutonium plutonium-239 undergoes fission with fast as well as slow. Fast as well as slow. Fast as well as slow neutrons. As well as slow neutrons. Note on that point, slow neutrons. Next point, uranium-235 and uranium-239. Uranium-235, uranium-239, plutonium are used as fuel. Are used as fuel in nuclear reactors. Are used as the fuel in nuclear reactors. Note on those points. Nuclear reactors. The way it will coming out from this is, that is 92 uranium-238 plus 0 and 1, then it goes to 56 A141, next one 36 krypton 92 plus 3 0 and 1 plus Q. Q means energy plus Q. It is not visible again. Okay, I am writing that point here now. I will continue at the same point. That is 92 uranium-238. 92 still. 92 uranium-238 plus 0 and 1. Then it goes to 56 Ba 141 plus 36 krypton 92 plus 3 times O and 1 plus Q. Q is called the energy. With this whole process, after completion, it generates an energy that is nearly or equals to 200 MeV. The value of the Q is the energy coming out. In the case of the nuclear fission process, the energy is how much it is? 200 MeV. About 0.1%. About 0.1% of mass of reactant is converted into energy. That is the description of the important term, that is the nuclear, that is the fission process. Only 0.1% of the mass reactant is converted into energy. Next, another point come under the same topic, that is prompt neutrons. I'll define PROMT, prompt neutrons. Because anything I have to take the subtitle, definitely first my interesting point is to define that particular term what I am writing on board. Now I have to define this one now. The first one is the neutrons. I have to define this one now. The neutrons are released immediately. The neutrons released immediately during the fission process. during the fission process is called, or if double R there, that is an are called, that is easy, are called prompt neutrons, are called prompt neutrons. That means the neutrons released immediately during the fission process is called prompt neutrons. The prompt neutrons are two characteristics are there. They are highly energetic. They are highly energetic. One of the point is highly energetic. Second one, not suitable for chain reaction. Not suitable for chain reaction. Not suitable for chain reaction. Now wait few minutes. Now chain reaction I will define separately. Now the prompt neutrons are, these are the things. The neutrons are released immediately during the fission process. They are called prompt neutrons. Characteristics of the prompt neutrons are highly energetic and not suitable for chain reaction. Not suitable for chain reaction. And go for the, what is the definition of the chain reaction? I tell you first. Chain reaction. Next one is now chain reaction. Chain reaction. Now first I define what is the meaning of this one now. It is self-sustained. It is self-sustained reaction. It is self-sustained reaction in which the products are capable of initiating similar reactions. In this process, this is called similar reactions. Two more points are there, then I will conclude that definition of the chain reaction. Those two terms are very, very important. Concern to this. Similar reaction. In this process, number of neutrons released increases in geometric progression. Increases in geometric progression. Geometric progression. That is the basic point should be highlighted here. That is the significance of the chain reaction. The cumulative increasing is not in ordinary multiplied form. Geometrical progressive wise the values are increased after the reaction. That is called chain reaction. Now the geometric progression value had to define one parameter, that is called the multiplication factor, that will decide that the nature of the reactions. Okay now? Now here one constant I am taken. K is called multiplication factor. K is called the multiplication factor. K what it defines now? Number of neutrons in present generation divided by number of neutrons in previous generation. Number of neutrons in present generation to the number of neutrons in previous generation. Number of neutrons in present generation to the number of neutrons in previous generation. From this now we are defining the values of one by one now. Now whenever K is less than 1, that is called under critical condition, under critical reaction. K is less than 1, under critical reaction. Next one now, K equals to 1 is called critical. K equals to 1 is called the critical. Now here what happening now? Energy is produced here. Energy produced at steady state. Energy is produced at steady state. That is K equals to 1. If K value is greater than 1, that is called supercritical. That state is called supercritical. The nature is here explosive. The nature of this explosive is not controllable. Explosive stage will comes whenever K greater than 1. Critical stage possible to control it some extent. That is called K equals to 1 is a critical stage. K is less than 1 under critical. It is not harmful to any area, that particular location where you want to apply the nuclear energy you want to release or to destroy that particular places. The amount of that kind of impression is very less. K is less than 1, K equals to 1, that is moderate level, and K is greater than 1 is not possible to control once this stage is reached by the nuclear reactor. Now these are the points are relevant to the topic that is called the nuclear physics. Okay, I'll close the point here now. I'll add some more points in the next lecture. Okay, thank you very much. Thank you.